In this video, we focus on a reaction called the acid-catalyzed hydrolysis of esters. In this reaction, what we are going to observe is that if we take an ester starting material, such as this, where keep in mind the R and R prime groups represent carbon chains or rings, we react it with water in the presence of acid as the catalyst to speed up the rate of the reaction. The product we'll observe is a carboxylic acid, where we have replaced the O-alkyl group of the ester with an OH group from water to give this carboxylic acid group in the product. The other product of this reaction corresponds to the O-alkyl group of the ester, OR-, bonding to hydrogen to give an alcohol product, ROH. So in other words, the reaction of an ester plus water yields a carboxylic acid plus an alcohol as the product of this reaction. Now, you may be looking at this reaction after viewing the previous video about Fischer esterification and saying to yourself, this looks kind of familiar. It looks like Fischer esterification in reverse. And you would be absolutely right, due to the fact that the Fischer esterification reaction is an equilibrium reaction where we reacted a carboxylic acid with an alcohol to give an ester as the major organic product. We can push that equilibrium back in the other direction by using water to provide the carboxylic acid product. So Fischer esterification and this reaction we're learning here, acid-catalyzed hydrolysis of esters, are the same reaction but running in reverse, where esterification runs in the direction toward the ester product. Acid-catalyzed hydrolysis is using water to break that ester bond and yield the carboxylic acid product. Both of these reactions, acid-catalyzed hydrolysis, which takes an ester and creates a carboxylic acid product, and the reverse reaction, Fischer esterification, taking the acid and creating the ester product, are both vitally important in biology. One example of that is in the field of fats and lipids, where fatty acids are carboxylic acid-containing molecules that within the body, through an enzyme-catalyzed reaction, are converted into esters referred to as triglycerides. And then, when it's time for the triglyceride ester to be broken down, an enzyme catalyzes the reaction to take it back in the other direction. So that reaction biologically is also acid-catalyzed, but in a biological system, the acidic properties needed are provided by an enzyme. So let's go ahead and take a closer look at acid-catalyzed hydrolysis of esters. One of the first questions that we need to address is we mentioned that this reaction represents an equilibrium, and we need to ask, how can we manipulate that equilibrium to favor either the carboxylic acid being most abundant at equilibrium or the ester? How do we force the equilibrium one way or the other, in other words? Well, in order to do that, we can apply a principle called Le Chatelier's principle. Le Chatelier's principle refers to a series of ways to perturb a system out of equilibrium in order to promote the formation and favoring of one side of this equation or the other. Le Chatelier's principle indicates a few different strategies for manipulating the equilibrium of a reaction, and I'll mention a couple of those here. One way to change the equilibrium of the reaction is to add an excess of one of the reactants. If you add an excess, which I'm going to abbreviate as XS for excess, of just one reactant, that will force the equilibrium toward the opposite side of the equation. So if we were taking this reaction and we wanted to favor the production of carboxylic acid, in other words, we wanted to create a lot of carboxylic acid, what we could do is add an excess of water. That's one of these two reactants, ester plus water. Water makes sense to add an excess logically because it's a very cheap reactant, and so from a practical standpoint, that's a good one to add. So if we add an excess of water to the reaction, that's going to force the equilibrium toward the side of the carboxylic acid. So if our objective is to create lots of carboxylic acid product, add excess of water to favor the production of the carboxylic acid. On the other hand, if the desire was to create as much ester product as possible, what we could do alternatively is add an excess of one of the two reactants on this side, taking our equation back toward the left. So we could add an excess of carboxylic acid or alcohol. By adding an excess of alcohol, for example, R'OH, that would allow us to favor the formation of the ester product, because whichever reactant we add in excess, the equilibrium per Le Chatelier's principle is going to favor heading toward the other side. In other words, creating lots of product from the other side of the equation. Another way that we can apply Le Chatelier's principle to perturb the equilibrium of the system and favor one product over another is to remove one product from the reaction mixture. And that will favor forcing the equilibrium toward that side of the equation. So this forces the equilibrium toward that same side of the equation. And an example of that in play is if we were to say we wanted to favor creating the carboxylic acid product. We could, assuming the alcohol has the lowest boiling point of any of the substances here, we could remove the alcohol by distillation, by boiling. And if we did that in this reaction mixture, that would push the equilibrium toward the side of the carboxylic acid product. So if we remove the alcohol by distillation, the reaction will favor the carboxylic acid side of the reaction. Because whatever product we remove selectively from the mix is going to force the equilibrium to come toward that side to create more of that product. Now, up until this point, we have worked with acid-catalyzed hydrolysis reactions using predominantly R groups and R' groups to denote the structures of the ester starting materials and the carboxylic acid and alcohol products. Here, let's now take a look at an example problem where we're tasked with looking at specific reactants and predicting what the major organic product of those reactions would be. Propyl acetate, we should be able to draw out. Remember that the acetate group is a carbonyl group with a methyl bonded, like so. And then propyl here in this name refers to the fact that we have a 3-carbon chain. This name that has two parts, the last part ending in ATE, and the first part being an alkyl group name, will represent an ester. So remember that esters are alkyl alkanoates as the way that those are named. So when you see the term ATE paired with the alkyl group name, that's going to tell us that this is an ester. So we have propyl acetate. We are reacting it with H+ or acid and water. And you may see an equilibrium arrow written here. You may also just see it written as an arrow going this way. Either or, don't let it fool you. We are going to be talking about an acid-catalyzed hydrolysis reaction. Also, it is not essential that the acid catalyst and the H2O both be written above the arrow here. You might see water written here alongside propyl acetate and acid catalyst written above. There's various permutations of that, and all of those are accurate ways to represent this reaction. So with propyl acetate drawn out, reacting with our acid catalyst to speed up the reaction, and water present, what we would expect as a pairing of an ester reacting with water is we predict that to be an acid-catalyzed hydrolysis reaction where the bond that breaks is going to be this bond right here. And that bond gets replaced with an OH group from the water molecule that comes in. And therefore, we can go ahead and draw out the products of this reaction. So we'll still have our carbonyl group bonded to the methyl, hence we still have our acetate group in place here. And now we've replaced the O-alkyl group from the ester with OH from water. So I'm going to draw in the OH in green here to match the color coding that I've shown above the arrow there. And then this part of the molecule here that has broken away, that is our oxygen plus our 3-carbon chain here of our ester, is going to become our alcohol product. And so I can draw that out over here as an oxygen bonded to a 3-carbon chain, and we'll have a hydrogen on it where that hydrogen is brought in through the reaction as well. And in the net equation, what we would see is that of this H2O, OH went here, and the second hydrogen went over here to give this product. So in cases of acid-catalyzed hydrolysis, the way that we can evaluate this is we are breaking the bond between carbon and oxygen of the ester. Once we break that away, this part here is what will become the alcohol product, or the R'(OH) in our abbreviated scheme earlier. And this carbonyl group plus whatever alkyl group is over here on this side of it is going to become bonded to an OH group here to replace what O alkyl group was lost in this reaction.